Okay, today we're going to learn about impulse functions and how to describe them mathematically, and then how to work with them in ordinary differential equations. So first of all, let's figure out what we mean mathematically by an impulse function. So suppose we have a pen that works. So suppose we have a function that that's zero on the interval from, let's say, from minus 10 to infinity, from minus infinity up to minus 10. Let's say it jumps up to the value 1, and then from till to 10, and it doesn't matter whether I put the point here or not. I'll do it this way. And then it becomes 0 after that. And let me get this to focus a little better. There we go. Okay. Okay. And so then it looks still a little blurry. There we go. Okay. So we start with a function that looks like this. So that means you can imagine that this is modeling something that switched off when x is in the range from, when t is in the range from minus infinity to minus 10, and from minus 10 to 0. And then it has the value 1 when it's in the range from minus 10 to plus 10. Okay, and notice whether you think of it like that or whether you think of it like a little step, you let it be multi-value. What's the error? And I'm saying this is the value. Well, let's see. I'm going to change this a little bit. This interval has length 20. So let me make this have height 1 over 20. Okay. And so what's the area under this curve? The area, you could do it by an integral, but it's a rectangle, so it's much easier than that. The area is the length times the width. So the length is from minus 10 to plus 10, so that is 20. And then the height is 1 over 20. So the area of this curve is 1, or the area under that curve, I should say, is 1. All right, now let's make it so that we have a function which is 0 up to minus 5. It jumps up to the value 1 over 10. So 1 over 10 is bigger than 1 over 20. This isn't going to look very much to scale. But as you all know very well, my artwork leaves something to be desired. Okay, so this is going to be 1 over 10. And you can see that's a higher rectangle than the one. It's narrower, but it's higher. Okay, and what's the area under this curve? Well, the width goes from minus 5 to plus 5, so the width is 10, and the height, I've made it to be 1/10, so the area under that curve is 1. And you keep on going like that. If I made the curve go now just from minus 1 over n to plus, make it look even, to plus 1 over n. So it's 0 out here and it's 0 out here. And now its height is n over 2. So it takes the value, the height of this rectangle is n over 2. And so now the area under this curve, the width is 2 over n, times the height is n over 2. So the area stays 1. And so what you see is that the skinnier this gets, the skinnier the bottom of the rectangle gets, the higher the top of the rectangle has to get in order to preserve the fact that the area is 1. Okay, so you could define a function, let me call it d sub tau of t, to be the function 1 over 2 tau if t is between minus tau and plus tau, and take it to be 0 otherwise if t is less than minus tau or t is bigger than tau. Okay, so that's the idea like this, but calling it tau instead of n. Okay, And it's clear that the area under such a curve, like we just argued, the area under the curve is going to be the integral from minus, it could go from minus infinity to plus infinity of d sub tau of t dt. But d sub tau is only non-zero on the interval from minus tau to tau. So that goes from minus tau to tau, 1 over 2 tau. So that's 1 over 2 tau times 2 tau. So that is equal to 1. Okay, so this function d sub tau always has the area under the curve being 1. Okay, so we'll remember that the integral from minus infinity to infinity of d tau of t dt equals 1. Okay, and another thing you notice is that you could set, you notice what happens to d tau as tau goes to 0 from above. As tau goes to 0, so tau is what we called n right here. So as tau goes to 0, um, tau is what we call 1 over n right here, I should say. So as tau goes to 0, this box is getting skinnier and skinnier. And so the value of this function is equal to 0 for all t not equal to 0. The value at 0 is a little questionable because what's happening as the width of this box gets smaller and smaller, the height or the value of the function at 0 has to get bigger and bigger. This is the graph of d1 over n of t. Okay, up there. Okay, so we have these two properties, the d tau. Okay, and now we define the delta function. And I put function in quotes because it really isn't a function at all. The delta function, right, is delta of t, is the limit as tau goes to 0 of d tau of t. Okay, so it's not a function because it has some funny properties and well, it's not a function. So in other words, delta of t, because this property has to hold for all um, I'm sorry, t goes to 0 from above. Okay. So delta of t is equal to 0 for all t not equal to 0. Okay. Because that's true for d tau of t as long as t is different from 0. And so if you just take this limit, by the definition there, that has to be true as long as t is not equal to 0. We're leaving open what happens at t equals 0. Also, because of property 1, so by 2, this holds. By property 1 of d tau, we see that the integral from minus infinity to plus infinity of delta of t dt is equal to 1. Okay, so you see this can't be a real, it can't be a bona fide function because delta of t is 0 everywhere except possibly at one point. Yet when you integrate it, you don't get 0, you get 1. That means it has to have infinite mass at t equals 0. And that's the only place we can get something non-zero, and it's by its very construction satisfies this property. This is what's known as the Dirac delta function by lots of people. But like I said, it's not a function at all. That's okay. And you can shift it. Sometimes it's useful to have a shifted version of that. Sometimes you want to look at delta of t minus tau. So this is equal to 0 for all t not equal to, I'm sorry, I said tau, t minus t0 for all t not equal to t0. And the integral from minus infinity to plus infinity of delta of t minus t naught dt is equal to 1. Okay. All right. Okay. So let's see what some of these funny properties tell us. Um, First of all, let's look at what is the Laplace transform of delta of t minus t naught. Okay, let's compute it. Okay, so the Laplace transform of delta of t minus t naught. Well, that's the Laplace transform by definition as a limit as tau goes to 0 from above of d tau of t. The Laplace transform of that. Okay, so that is equal to the limit. Now the Laplace transform is continuous, a continuous functional. So this is the limit as t goes to 0 of the Laplace transform of delta tau of t. So that's the limit as tau goes to 0 from above. All right, by definition, this is the integral from 0 to tau to infinity of e to the minus st del d sub tau of t minus t naught dt. Okay. All righty. So that's not real convenient for us. Um, well, let's make a change of variables. Well, first of all, let's write out what d delta tau is. D tau rather is. So this is a limit as t goes to 0 from above. Now d tau is 0 except when you are between t naught minus when t um, yeah, let's make the change of variables first. Let me uh let me let okay okay. So we're going to go, this is the limit as tau goes to 0 from above of the integral of, okay, so what is what is the value of d tau of t minus t naught? It's going to be 1 over 2 tau when t minus t naught is between minus tau and plus tau. So this is going to be 1, you'll have an e to the minus st. It's going to be 1 over 2 tau when t, when minus tau is between t minus t naught and plus tau. Okay, so that says as far as t goes, that means we have t naught minus tau is a lower bound for t, and t naught plus tau is an upper bound. So this is the integral from t naught minus tau to t naught plus tau, because d sub tau is 0 otherwise. And then you have dt. Okay. Now, as far as t goes, um, uh, tau is constant. So this will be the limit. Sorry, that was on the side there. So this is the limit as tau goes to 0 from above of, okay, now you do the integral with respect to t. So you just get an e to the minus st divided by 2 tau s evaluated from tau t naught plus tau to t naught minus tau. Okay. And so this will be the limit as tau goes to 0 from above. You will get e to the minus. All right, now we're replacing, this is a limit on t, so we will get e to the minus s t naught plus tau over 2 tau s minus e to the minus s t naught minus tau. Okay. All right, which is which is now you notice that you have a common factor of e to the minus st naught in both of these terms. So let me pull that out in front because that has nothing to do with the limit. Okay, so that's a minus st naught. Now you take the limit as tau goes to 0 from above. You have e to the minus s tau minus e to the, this will be the s tau over 2 tau s. Let me write that as, now let me be careful. This should be, oh, I left off a minus sign when I integrated because you have e to the minus st. That's my problem. So this is a minus and this is a plus. This is a minus and this is a plus. And now I'm dividing by 2 tau s, but I'm going to leave the 2 in here and put, well, let's leave this here. Let's just leave that there. Okay. Okay. And now you notice that this e to the s tau minus e to the minus s tau over 2 is sinh s tau. And then we divide by tau s. Okay. All right, and now you want to take the limit as tau goes to 0. But as tau goes to 0, we can use L'Hopital's rule because you get 0 over 0. So by L'Hopital's rule, this is e to the minus s t naught times the limit as tau goes to 0 from above. The derivative of sinh is cosh. So we get cosh st, and I'm taking a derivative with respect to tau, so I get a factor of s. When I differentiate the denominator with respect to tau, I just get s. So the s's cancel. And as tau goes to 0, you get cosh. Cosh at 0 is 1. So this becomes e to the minus st naught. Okay. So what we showed in that long calculation is we just proved, whoops, I have something written on here. Okay. So we just showed that the Laplace transform of delta of t minus t naught is e to the minus st naught. Okay. Okay. So we computed the Laplace transform of this delta function. Okay. Let me show you another reason why the delta function is not a function, or let me say one of its strange properties. How about that? So here's a theorem. The integral from minus infinity to infinity of delta of t minus t naught at times any function that you can integrate. So any integrable function. So all continuous functions, piecewise continuous, all that good stuff, and more actually. That if you integrate that against the delta, you take an integrable function, you integrate it against the delta function at t minus t naught, you get the value of the function at t naught. Okay. All right. So why in the world would that be true? So look at, when you look at this left-hand side, okay, that's the limit as tau goes to 0 from above of the integral from t naught minus tau for the same reason that we gave in the previous argument from t naught plus tau of, because you write this guy, so you write this as the limit as tau goes to 0 from above of d sub tau of t minus t naught, right? And so that's what I do. That means my limits go from t naught minus tau to t naught plus tau 1 over 2 tau times f of t dt. Okay. That's using the definition of d tau, like we did in the previous calculation. Okay, and now you're kind of stuck. So what do you do? What you do is you use the mean value theorem for integrals from calculus 1. And what does the mean value theorem for integrals say? It says that the integral from a to b of a function is equal to the basically the average value of the function. So this will be 1 over 2 tau times f of tau, or f of t. It's it's the value of the integrand at some intermediate point in the interval times the length of the interval. So the length of the interval is t naught plus tau minus t naught minus tau. So that is an interval of length 2 tau. So that's the length of the interval. This is the integrand at some intermediate point. So this is for t star in between t naught minus tau and t naught plus tau. Okay, that's exactly what the mean value theorem for integrals tells you. You can look that up if you don't remember it from calculus 1. So now what you see is that the 2 tau and the 1 over 2 tau, so this is the length of the interval. This is the average value or the value of the integrand at some intermediate point. And so the 2 tau and the 1 over 2 tau cancels. So this just becomes the limit as tau goes to 0 from above of f of t star. Okay, but what happens to t star as tau goes to 0? As tau goes to 0, t star, whoops, sorry, you can't see that. All right, okay, so we had this is the intermediate value theorem, and t star has to be between the two endpoints of the interval. So now the 2 tau and 2 tau cancel. So I just get an f of t star. I take the limit as tau goes to 0. But what happens as tau goes to 0 to t star? T star is sandwiched below by t naught minus tau, above by t naught plus tau. So as tau goes to 0, this just goes to f of t naught. And that's what you had to show. Okay. So that's the funny property. I won't be asking you to prove any of these. Um, you just have to know how to work with these things. Okay. So the delta function models an impulse force. It's 0 for all time, and at the second you want it to hit, or a t at the when the argument of the delta function is 0, it switches on for that second and has infinite mass at that one point, satisfying all these unusual properties that we just saw. So it comes up a lot in different engineering applications because it's a very useful way to model impulses. So let's look at what happens when we try to do a delta function in an ODE using Laplace transforms. Now, another reason Laplace transforms are useful is because you can do problems with delta functions as inhomogeneous terms, and that's very hard to handle by any other method. In fact, no other method that we've seen up to this point would be able to handle these kind of impulse functions, these kind of delta functions. So if you remember way back when we started doing this, somebody asked, could I motivate this? And one of the reasons is because you can you can solve ordinary differential equations with discontinuous functions and impulse functions as inhomogeneous terms, and you couldn't do that by any other method. Okay, so suppose we want to solve this ODE. What do we do? All right, so we're in the section on Laplace transforms. We're going to Laplace transform both sides. So take Laplace transform on both sides. Okay, so when we do that over here, we get 2 times s squared capital Y minus sy of 0 minus y prime of 0 plus the Laplace transform of y prime, which will be sy minus y of 0 plus 2 capital Y is going to be equal to the Laplace transform of the Laplace transform of the delta function at t minus 5, which by what we showed before or by the table is e to the minus 5s. Sorry, s is the transform variable. So that's e to the minus 5s. Okay. All right, so let's see. What do we have then? We have y times 2s squared. Y of 0 and y prime of 0 are both 0. So this goes, and that goes. So I have a 2s squared plus s plus 2 is equal to e to the minus 5s. So y of s is e to the minus 5s over 2s squared plus s plus 2. Okay. Okay, and so let's think of this as e to the minus 5s times g of s. So g of s is 1 over 2s squared plus s plus 2. All right, so how am I going to do the Laplace? And I need to do the inverse Laplace transform, of course. So how am I going to do this? Well, I'm going to complete the square in s because this one doesn't factor. So that means I need a coefficient of 1 in front of s squared. So I'm going to write this as 1/2 1 over s squared plus s over 2 plus 1. Okay. So now when I do that, I have the 1/2. And here I take half the coefficient of s. So I'm grouping these two together. Take half the coefficient of s. That'll be 1/4. When I square it, I'll get 1/16. So that's a 1/16. I added in, so I have to subtract 1/16 here. Okay. So this becomes 1/2 1 over s minus, s plus 1/4 squared plus 15 over 16. Okay. And so now when I want to look that up on the chart, um, you need the right, you think of this part as s minus a squared plus b squared. So I can't have a 1 up there. I need the square root of this guy. So I need the square root of 15 over 4 up top. So I better multiply by the constant 4 over the square root of 15 to compensate for that. So now I have 2 over the square root of 15, putting my constants together. Whoops, sorry, that's not a 1. It's the square root of 15 over 4, s plus 1/4 squared plus 15/16. Okay, so g of t, the inverse Laplace transform of that, leaves that constant alone. And now when you take the inverse Laplace transform, you will get e to the minus t over 4, because at a is minus 1/4. And then you get sine of b, which is 15, square root of 15 over 4t. Okay, so that's the inverse Laplace transform of g, but little y of t, which is the inverse Laplace transform of capital Y of s, is the inverse Laplace transform of e to the minus 5s g of s. And so by that row 13 on our chart, that is going to be 2 over the square root of 15, u sub 5 of t, and now e to the t minus 5 over 4. I'm sorry. Yeah, this is t minus 5 over 4 with a minus sign times the sine of square root of 15 over 4 times t minus 5. Okay, so that's an example of one with a delta function in it.